Hi everybody, my name is Hana Ahmadi. I'm a third year PhD student at the University of Calgary, working under supervision of Professor Apostolus Kansas and Professor Stephen Bryant. This video shows you a study on flow dynamics of magnetic pickering nanoemulsion in porous media. To talk about the background of this research, I've got to say that employing multi-fractured horizontal well has become a widely adopted technique for effectively extracting resources from these low permeability tide reservoirs. A significant challenge in this domain lies in effectively characterizing the fracture network within shale oil and gas reservoirs, which is crucial for accurately assessing fracturing operations and evaluating the potential efficiency of different enhanced oil recovery protocols in unconventional reserves. As a result, tracer injection along with the fracturing fluid and flowback chemical analysis is a promising approach for fracture characterization. In this work, we want to propose a new tracer as a pickering nanoemulsion. So we can say that pickering nanoemulsions are investigated as a potential alternative for tracer injection to characterize the fracture during the flowback analysis in tight reservoirs. So the type of a nanoparticle that we use in this research is iron oxide nanoparticle, and the advantages of using this nanoparticle is being super paramagnetic with the ability to be detected in situ, easily synthesized, controllable size, strong stability, minimal retention in fracture, environmental benign feature. Consequently, this study investigates the impact of magnetic nanoparticle coating ratios on the transport behavior of magnetic nanoemulsion in porous media using dynamic city imaging and various effluent tests. To talk about the methodology that we used in this study, I have got to say that first we modify our nanoparticle by coating them with a polymer. In order to do that, we use a homogenizer, sonicator, and centrifuge to make different samples. The coating ratio that we use here were in different types, like 0.5 to 1, 1 to 1, 2 to 1, 3 to 1, and 4 to 1, which is the ratio of polymer to nanoparticle that we use to investigate the effect of coating on the transportation behavior of nanoemulsion in porous media. And then by mixing 1 weight percentage of polymer coated iron oxide nanoparticle, 10 volume percentage of oil, and the oil that we used was dodecane, and deionized water, and mixing them with homogenizer, and after that applying energy with sonicator to disperse oil in the system and making a nanoemulsion. We did our flooding test with the setup that you can see here in this part, and our setup had different parts, like a pump to inject nanoemulsion and water. We had two transfer vessels for holding nanoemulsion and water, then pressure transducer at the inlet of the sandpack, CT scanner, inline densiometer at the outlet, and we collect our effluent with the effluent collector. In this experiment, we inject 2 per volume of nanoemulsion and then wash it with 5 per volume of water. And at the beginning of the experiment, first we saturate our sandpack with water and then invade it with nanoemulsion and then chase water flooding. So after doing the experiment, we collect all the results and then interpret all of them. And here in the results part, you can see some results from the experiment. So first of all, you can see the effluent saturation profile obtained from density. So we use density of effluent, density of nanoemulsion, and density of water to normalize the effluent density and draw this graph. and it demonstrates how the nanoemulsion saturation profile develop as a function of injected pore volume during this flooding process. For all the experiments, I mean the different ratios like 0.5 to 1, 1 to 1, 2 to 1, 3 to 1, and 5 to 1, that I named all of them as M1, M2, M3, M5, M4, and M5. So initially saturated with water, the sandpack gradually experienced invasion by the nanoemulsion. During nanoemulsion injection, water production was observed during the breakthrough of nanodroplets occurred at approximately 1 per volume for all experiments. The subsequent increase in the saturation profile indicated nanoemulsion breakthrough. So by continuous injection of the nanoemulsion led to complete saturation of the sandpack with nanoemulsion, as the line is equal to 1, as evidenced by the effluent saturation profile matching the nanoemulsion saturation baseline. During the chase water flooding, the saturation profile gradually decreased, ultimately approaching to the initial water saturation. However, the saturation profile didn't align with the water saturation line, indicating the presence of oil droplets in the effluent throughout the experiment. This trend was consistent across all experiments, indicating that the nanoemulsion was progressively displaced from the sandbag. The immigration in the saturation profile reflects the dilution and removal of the retained nanodroplets, eventually reaching the density of the injected water, thus confirming the effectiveness of the chase water flooding in displacing the nanoemulsion. As you can see in this figure, nanoemulsion production persisted during chase water flooding up to 2.2 per volume for M1, 3.2 per volume for M2, 2.7 per volume for M3, 3.3 per volume for M4, and 3 per volume for M5, as indicated by the saturation measurement during the chase water flooding, aligning closely with the nanoemulsion saturation baseline. This consistent saturation suggests stable production of the nanoemulsion. However, in experiment M1, the saturation profile during chase water flooding was relatively lower than the baseline nanoemulsion saturation from 2.2 here per volume to 3.2 per volume. This discrepancy suggests that the nanoemulsion produced at the 0.5 to 1 coating ratio had a lower oil content due to its reduced stability, indicating that a portion of the nanodroplets had been retained within the porous media. This observation is consistent with the higher pressure drop observed during chase water flooding, constraining with the more stable nanoemulsion with coating ratio of 3 to 1 and 4 to 1. That we want to explain about that in the next step. The eventual return of the saturation profile to the water baseline saturation in all cases indicates that water had established its path through the sandbag and no further nanoemulsion production occurs. And in the next graph, you can see the pressure drop for all experiments during both nanoemulsion flooding and water flooding. So I have got to say that for all experiments, pressure drop builds up as the nanoemulsion invades the water-saturated sandpack up to 2 per volume of nanoemulsion injection. This phenomenon is attributed to the nanoemulsion's higher viscosity than water, which mitigates the tendency for viscous fingering. Consequently, the pressure drop decreases and stabilizes at a constant value when water invades the nanoemulsion through the sandpack during chase water flooding. M2 exhibits the highest pressure drop, reaching up to 8.89 psi due to the lowest initial permeability of the sandpack. As you can see here, For M1, M2, M3, stabilized pressure drop is double compared to M3 and M4. So I should say that this is attributed to the thinner polymer coating and the nanoparticles, which result in higher hydrophobicity of the polymer coated particles and lower stability. The lower stability in porous media results in increased flow resistance and higher pressure drop. So in the next graph, you can see nanoemulsion and water saturation profile for the experiment 4 to 1, as the experiment 4 to 1 is the most efficient experiment. So I put the result for them there, here, and you can see the saturation distribution profiles of nanoemulsion and water in the co-current flow of nanoemulsion and water. The first one is on the top is the nanoemulsion saturation, and on the bottom you can see the water saturation during the flooding. The saturation profile during the nanoemulsion flooding and post-water flooding are uniform. As you can see here, this pattern reflects the progression of the nanoemulsion front as it displaces the initial water phase, confirming the effectiveness of the injection process in fully saturating the sandbag with the nanoemulsion. During nanoemulsion flooding process, the nanoemulsion concentration increased into the sandbag. The migration front dispersed through the pore, penetrating deeper into the medium. These nanoemulsions exhibited a piston-like movement along the sandbag, resulting in full saturation after 1.4 pore volumes of injection. The nanoemulsion flooding process continued up to 2 pore volume, followed by 5 pore volume of a water injection to displace the nanoemulsion with a less viscous liquid phase. Before the water phase breakthrough, during the water phase flooding, an inclined front between the two phases of a water nanoemulsion is observed with a greater saturation of water at the top half of the sandbag due to the gravity override. In other words, the water displacement was relatively uniform at the sandbag inlet and become more channeled with the bypass nanoemulsion further downstream. You can see these results here. As we interpret the city images, the green color represent water, and the red color represent nanoemulsion, and this is the channeling of water when we inject the water in the sandbag. So as a result, we can say that by increasing the coating ratio, the stability of a nanoemulsion just increases, and it can move through the sandbag very easily, and we can recover all the nanoparticle and nano droplets that we inject into the sandbag. Thank you so much for your attention.